Welcome to the lectures on modern digital communication techniques. So far we have seen the transmission of signal passing through an AWGN channel as well as the receiver structures, where we have looked at the first part of the receiver, which consists of the demodulator. We are now going to look into the next part of the receiver, which will complete AWGN receiver. So the next part of the receiver will be the detector. As discussed in the previous lectures, that the demodulator could be realized in two possible ways. One is the correlator, the other is the matched filter. In the correlator version, we use the basis functions on n dimensions, that means the n different dimensions of the transmitted signals, and correlate the incoming signals with each of the basis functions. Or in other words, we project the signal onto the basis functions and we get the components of the signal on the dimensions. In case of matched filter, we say it is a filter realization and the impulse response is matched to the basis function, where if h t is the impulse response, it should be equal to f k of capital T minus t small t, that is the flipped version of the signal. We also saw that a matched filter with this kind of an impulse response, which is matched to the signal, produces maximum signal to noise ratio at the sampling interval of small t equals to capital T, where capital T is the symbol duration. So what we have shown is that if you would set the impulse response which is matched to the signal, you are going to get the maximum signal to noise ratio. In both the cases, the received signal is decomposed into its components and we have the vector r as components with r1, r2 up to rn. And we explained briefly in the previous lecture that these components consist of the component of the signal as well as component of the noise. And we said that since a signal can be decomposed into the directions of the basis functions, so once we have the components of the signal, we can reconstruct the signal or we can identify which is the signal. So now at the receiver, we have the signal components which are corrupted by noise, and the job of the detector would be to identify which of the possible m signals does this particular vector represent in the best possible way. So we move on to our discussion on the optimum detector, and we said that the optimum decision rule is to be based on the observation of the vector r, and for this case we assume memory less transmissions. That means we do not assume with memory transmissions, and our aim is to design a signal detector which makes a decision on the transmitted signal in each signal interval based on the observation of the vector r, such that the probability of correct decision is maximized. And we explained qualitatively why do we call it as the decision process, because we are choosing one of the possible outcomes, one of the possible waveforms. So with this we move on, and we have the aim as stated that we have to create a decision rule, and this is based on the computation of the posterior probabilities. Now why it is so? Because we already have observed a particular signal. Based on the observation, we want to know what has been transmitted. So what was there at the source based on what has happened after passing through the channel. That is why we call it the posterior probabilities. So we basically have to calculate probability of signal S m was transmitted based on r, where m could be 1, 2 up to capital M. So that means you have to calculate these probabilities for each of the possible signals based on the observation r, and so we indicate this particular probabilities as p Sm given r. So this is the notation that we use, and the decision criteria is select the signal Sm. So you have to select the signal Sm for which this probability is maximized. So what we are saying is, you have observed r, you have to calculate the probability of any of each of these signals given r. So that is why we have these posterior probabilities. What you could have done what you generally have is, given a particular signal, what is the probability of R. So, we are going in the reverse direction, that is why we call posterior probabilities. So, the decision criteria is select the signal Sm for which these probabilities are maximized. So, that means we have to calculate these probabilities for m equals to 1, 2 up to capital M. So, to calculate all these probabilities. So, for that value of m for which this probability is maximum, we will be choosing that value of m as the solution. So, this kind of criteria is hence known as the maximum a posteriori probability criteria, and this kind of receiver is denoted by the MAP rule, maximum a posterior probability maximization criteria. So, this is the rule, that is what we are going to follow. So, to proceed with this, we have to start looking at what does this particular expression tell us. So, we use the Bayes rule. So, we have on the left hand side P Sm given R, because R is observed. So, we have to find all possible Sm, find the probability for all possible Sm and then choose the best of it. So, to evaluate this, we expand this expression using Bayes rule, where P probability of Sm given R can be expanded as probability of R given Sm multiplied by probability of Sm. So, this gives the joint probability of R and Sm upon probability of R. So, in another way you could also see P of Sm given R times P R is the joint probability of Sm and R, and this is also joint probability of Sm and R. So, that is a very short revision. So, anyway, this is by the Bayes rule we have this expression, and where P of R given Sm is the conditional PDF of the observed vector given Sm, and we have calculated this given the expression when we computed the output at the output of the matched filter, because R is the vector at the output of the matched filter, and PSM is the prior probabilities of the mth signal being transmitted. So, if we have a constellation, let us say with two symbols S1 and S2. So, all we are saying is that probability of S1 is P S1 and you have P S2 as probability of S2. Now, generally as we said earlier, if we want the mean to be 0, mu to be 0 in one of the earlier discussions, we said the constellations have to be symmetrically placed and they have to be chosen with equal probability. Now, you can make 0 with some other probabilities also. In that case, the probabilities would be having non-equal values. So, in either case, P of Sm is the prior probabilities. That means, in general cases, generally these probabilities are equal, but there could be situations where these are unequal. And if you look at P of R could be expanded as P of R given Sm multiplied by probability of Sm. So, that means we are taking, suppose you choose S1 and then you get P of R given S1, right, multiplied by P of S1 plus P of R given S2 times P of S2. So, that means you have averaged it over all possible transmitted signals. So, that is P of R. So, you could also see that P of R is independent of Sm, because you are taking over all possible Sm, you have already averaged over all possible Sm, right. So, P of R is not dependent on Sm, it is just the probability of observing a particular output. So, that means if we have to maximize this probability, we can see that the denominator term is almost irrelevant for us. All we are left with is the numerator term. A similar situation we had used when we discussed the properties of matched filter, and there also we had found that if we could hold the denominator constant, we could maximize the signal to noise ratio at the output by maximizing the numerator. So, although these are two different contexts, but we have a similar situation of operation over here. So, in this expression we do not need to consider the denominator part, because it will be common for all Sm. So, we will concentrate on the numerator part only. So, going ahead, so therefore, what we have with us is maximize. So, what we want, what we have represented over here is argmax. Argmax means the argument which maximizes this particular expression. So, the argument which maximizes is we are taking Sm as the argument. So, our outcome will be Sm star. You could say Sm star, you could also say M star, that is the index, right. So, we want to choose this. So, now instead of maximizing the whole expansion of this, we just concentrate on the numerator part, what we discussed over here. So, we are now concentrating only on the numerator part and going by the MAP criteria. So, you have to maximize P of R given Sm, which is relatively easier to do, and multiplied by P of Sm, right, because you have considered the prior probabilities of Sm. As we just said that it is highly possible that P of Sm are equiprobable. With this particular example, we said that probability of sending S1 is half, probability of sending S2 is half. So, that means they are equiprobable. So, P of Sm should be equal to 1 upon 2. If there are m such possible waveforms, if there are m such possible signals, and if they are equiprobable, then P of Sm is 1 upon m. And then again you take a look at this particular expression. So, what you will find is that this portion of the expansion is equal to 1 upon m, which is not dependent on small m. That means, it is not dependent on Sm. So, you have to maximize this, choose the argument which maximizes this. This part is no longer dependent on Sm if the signals are equiprobable, that means they are equally likely. So, in such a situation, so if we proceed with the case that if they are equiprobable, we would simply put P of Sm as 1 over m and we are left with this term. Again, since we are talking about maximization over the argument Sm and this is not a function of Sm, we need not consider this term, we can drop this particular term. So, what we have is P of R given Sm. So, all we need to find is P of R given Sm over all possible Sm, right. So, whichever maximizes this, whichever Sm maximizes this would be our choice of our answer or our solution. So, since the conditional PDF P of R given Sm are usually called the likelihood function, I can briefly tell why do we call it the likelihood function. Therefore, the receiver is known as the maximum likelihood criteria receiver. So, also you can write it as the ML receiver, right. And just at this point I would find it pertinent to remind you that there is a MAP criteria which is distinct. We will of course come across this again. The difference between the MAP criteria and the ML is clearly visible over here. In the ML, the maximum likelihood criteria, we have all signals with equal probability and therefore, P of Sm is no longer used, as you can clearly see in this expression, whereas in MAP criteria P of Sm is used. So, if the signals are equally likely, equiprobable, in that case these two expressions will be the same, would give the same output. The expressions will not be the same, but they would give the same output. So, that means the MAP and ML would result in the same solution. So, if we know that signals are equiprobable, we do not need to use this part, we only use this part of the expression and therefore, we have the ML receiver. So, with this we proceed with our discussion about the ML receiver. So, we have been discussing the AWGN channel. So, let us continue with this. In case of AWGN channel, I have opened this part because we have P of R given Sm. The likelihood function P of R given Sm is given by this expression which you have seen before. So, the difference or probably the slight change that you might see is we are using P of vector R given vector Sm. Now, this consists of P of R k given Sm k, that is what we had seen before, and we had calculated that P of R k is independent of P of R m. That means, for two different components we found that they are independent. So, the joint distribution we found it as the product of the marginal conditional distributions, and therefore, it is a product of those distributions. If it is a product of n marginal conditional distributions, then we have in the denominator pi n naught to the power of n by 2, where for each case it was just a square root, and for each case P of r k s m k we had e to the power of minus r k minus s m k squared by n naught. So, now since you have multiplied all this r k because of joint distribution, in the numerator we have got the summation, because e to the power of minus alpha times e to the power of minus beta times e to the power of minus gamma comes out to be e to the power of minus alpha minus gamma minus beta and so on and so forth. So, this is the expression of the P of r vector given S m vector. Remember, we had used underline to denote the vector notation, where S m is equal to S m 1 up to S m n. Similar for r k, this is equal to r 1 r 2 up to r n, right. That is what we had used. Okay. So, now if you look at these expressions, this expression is looks a bit cumbersome. So, to reduce the computation, what we can do is we can use the log of this function. Now, briefly we said that we can discuss the likelihood. So, suppose this is x and we have some PDF. So, this is P of x conditioned on, let us say, some parameter theta. So, this is the PDF and let theta be the mean of the PDF, suppose. So, there we have the mean of the PDF. So, if I change theta to some other value, so this is P of x conditioned on theta 1 to some other value, I can get the PDF which goes like this as theta 2, and this can be P of x conditioned on theta 2. So, now what we have is, in this particular thing, x is already observed. If you look at P of r given S m, r is the received vector. So, we already have some of the values. So, we already have some of the values, right. So, when I put it back into this PDF, PDF is no longer a probability, it can be now read as a function, because probability would mean that what is the probability, that means we are reading on the x on the y axis. But now we say that we have already observed these values, there are a whole set of values, and I want to treat this as a function. So, when I feed back all these values into the function, it is now a parameter of theta. So, I can have this function of theta of all these average values, and my objective would be to find the theta which is the best fit for all these set of values of x that I have got given this kind of a function. So, generally these kind of expressions are known as the likelihood function, because they are constructed out of the PDF. So, because given the function, we know that the curve should look like this, and therefore, we would like to find the value of theta for a given set of x values which is closest matching to that function. So, that is why it is called the likelihood function, and when we take the log of it, log of this likelihood function, it is called the log likelihood function. So, instead of maximizing the likelihood function, you can take the log of it, because log is a monotonic function. So, maximizing this would give the argument of it that maximizes this would be the same over here. So, taking the log of it, natural logarithm, you are going to get minus n by 2, that is over here in the denominator, ln pi n naught, which is straightforward, and since this is e and we are taking a natural logarithm, this would come straight down. So, you have the expression which is in the exponent of e. So, now we said we want to maximize this. So, if we have to maximize this, then we started with maximization of this, therefore, maximization of the log likelihood function, and now let us look at the log likelihood function. In the log likelihood function, we again see that this particular part is not influencing our result. This particular part is constant for all S m. whereas this part has Sm. So, if we want to maximize this, since there is a negative sign and we take this particular part separately, it is as good as minimization of this section, this part of the expression. That means, if I could minimize this part, again since n naught is constant, not dependent on m. So, I could take minimization of this particular part, right. So, that means, we could write maximization of the log likelihood function is same as find the vector Sm that minimizes this particular expression that we have. Now, if you take a careful look at what this expression means, it is component wise difference squared and sum over all components. So, clearly it is the distance of the vector r from the vector Sm. So, if we say I want to maximize this, which is maximization of this, which is produced by minimization of this term. So, that means minimization of this term is minimization of the distance of the vector r from the vector Sm. So, what we are trying to say is that we want to find the vector Sm which is closest to the vector r. So, that is why we call this particular expression the Euclidean distance, and our algorithm or our result is to find Sm that is closest in distance to r, and this is could also be claimed as the minimum distance detection accordingly. So, we are still in the detection problem. So, we have let us say 4 constellation points, and whatever we have received in the vector form is suppose here, right, and it has produced a component there and it has produced another component which is there, if you take this. So, now you have to find that which of these points are closest to this. Clearly, in this particular case we find that this constellation is closest to this, and hence we would choose this as our possible transmitted signal. So, that is what it means, right. So, further moving ahead, what we could also see is that this d that we have discussed here, d expression, we expand this d expression, that is the distance, and it turns out to be the length of the vector minus the inner product, you could see this as the inner product, plus the length of the vector of Sm. So, this is written in the vector notation, length squared, and what you see is that this is common to all Sm, this is not dependent on Sm. In the same manner, we may ignore this while computing the distance component, and what is left with us is the projection of r on Sm. So, you are projecting r on Sm and there is the energy of the signal, right. So, what we have is projection and energy of the signal which is relevant for us. So, since we do not need this, we modify the expression of d and we suppose mark it as d prime of r and Sm. So, which could be read as minus 2 r dot Sm, that is the inner product, and norm Sm squared. That means, we need to find Sm that minimizes this metric. So, we have to find Sm that minimizes d, which is same as find the one which minimizes this expression, right. So, d minimization, since this is a positive term, is the same as minimization of the rest of the term, because this is not influencing. So, if we look at d prime, we could also say that instead of minimizing this, we could also write it in by changing of notation of sign. We could say you could maximize 2 r dot sm minus norm sm squared, right, because we have simply multiplied by a minus sign. So, instead of minimizing something, it is maximizing the negative of it. So, now if we interpret this, there is a projection of r on sm, this project r on each sm. So, we have to try for different values of m, and hence r dot sm can be also read as the correlation metric. Correlation of r on sm we have to do over each sm. So, the correlation metric in the signal notation form, you could write it as whatever we have C over here as 2 times integrate r 0 to capital T r t times SMT, that is projection of r on this particular vector, take away Em, which is the energy of the signal, right. And this particular expression, now you could visualize it in form of a block diagrammatic representation similar to the earlier structures that we had seen. So, what we can have with us is the received signal, we will use the expression that is present with us, and just for the sake of seeing it on the same screen, we have the received signal coming in, received signal being split, and in the first path it is getting multiplied with S1, that is what we have, R with S1, and then there is the integrator. So, there is the integrator, and then you sample it at small t equals to capital T, because you have to read it up to capital T, because this SM is valid for capital T. So, remember we had always stated that our decision rule is for this interval, and our signal SM is also valid for this interval, and then I would take away the energy. Now, since we have a 2 over here, so in this particular realization we do not put a 2. So, therefore, when we take away the energy, we take away half the energy. So, you could have multiplied here 2 and you could have taken away the energy itself, this would have resulted in the same expression. So, just try to follow how we have converted from vector notations and finally reach the integral form, and which can be realized in this way. So, again as you see, it is for SM. So, that means we have to do for all m and find that m which would maximize this C. So, we could represent this diagrammatically in the form that the received signal gets correlated with all the different SM, right, the m possible signals. You may note this may be a bit confusing with what we had studied before, where we had taken projection of R on the different dimensions of the signal. Here we are projecting on the different signals themselves directly, and we have these components. So, you could do it in the vector form as here, or you could do it as here, or you could do it in the integral form. When you read in the integral form, you get it in this form, and then what you have are the different outcomes of the correlation of the received signal with the different possible waveforms, and then I would select that particular outcome which is the maximum. So, which is represented over here as the highest possible signal, and that will be the decision output. So, if this branch produces the maximum output, my selection would be the signal S2 was sent. And as we would like to see in the constellation diagram, if there is or a waveform diagram, suppose I have a waveform like this, and let us say I have another waveform like this, and what I receive is a noisy version. Let us say I receive something like this. So, what it tells you is you have to correlate this signal with S1 and with S2, whichever correlation gives the highest output, you choose that particular signal as your desired signal. So, that is how a detector would work. So, up to this point we have at least taken a complete view of a transmitter when the signal goes out of the transmitter, passes through a channel, enters the receiver, exits the matched filter or the correlator receiver, and then goes into the detector, and we have seen the detailed architecture of how the correlator or match filter works as well as a detector works. Thank you.